Hello and welcome from the Perimeter Institute for Theoretical Physics. My name is Kate Lunau. I'm a science writer, and I'm here with our panel today. Welcome to our audience in Waterloo and also our audience watching online. We're here on a historic day. We heard some really exciting news this morning from the LIGO scientific collaboration. They have detected for the first time gravitational waves, which are ripples in the fabric of space-time that were predicted by Albert Einstein 100 years ago. So this is a very big day, and I'm here with 4 experts to discuss what it means. Before I introduce our panelists, I just want to say that if anyone watching has any questions, we have Perimeter experts manning social media, Facebook and Twitter, so please feel free to get in touch. Now let me introduce our panelists. On my far right is Asimina Arvanitaki, a particle physicist with special interest in gravity, dark matter, and dark energy. Her work draws on various fields of physics to propose new theoretical and experimental approaches to long-standing problems. Next, we have Latham Boyle, a cosmologist at Perimeter Institute. His work focuses on gravitational waves, black holes, and what that can tell us about the early universe. He's also worked to conceive new designs for future gravitational wave telescopes. Here is Luis Lehner, Deputy Faculty Chair at Perimeter. As a specialist in strong gravity and numerical relativity, he creates numerical simulations to help understand gravity in its extremes, such as around black holes and neutron stars in 4 dimensions and higher. And next to me here is Neil Turok, director of the Perimeter Institute. He holds the Mike and Ophelia Lazaridis Niels Bohr Chair at Perimeter. A cosmologist and author, his work focuses on developing fundamental theories of cosmology, such as the cyclic model for cosmology, which he co-developed, and proposing new observational tests. Dr. Turok is also the founder of the African Institute for Mathematical Sciences. So I have a great panel here today, and we're certainly going to have a very interesting discussion. We're going to kick off, to start with a short video that will give some context to the news that we heard today.
Gravitational waves are ripples, not in air, not on a pond, but in space-time itself. And they're generated by massive objects moving around, like binary black holes or neutron stars.
Theory told us from the days of Einstein that there could be black holes. It told us that if there are black holes or other dense objects, they will emit gravitational waves. So this has been known for almost a century.
The real complication is they're just so damn hard to see. So they can carry lots of energy, but because gravity is weak, the gravitational waves tend to be very difficult to measure, and that's what's changing now.
We have been for years trying to both detect gravitational waves. We have seen them in some sense indirectly, the effect they have in some binary systems like the Pulsar or the Hall-Taylor binary pulsar. We can now begin using gravitational waves to open a new window to the universe.
It also opens a window, I think, on the dark universe. So astronomers have for the past 10,000 years been studying the light side of the universe. And contrary to what modern cinema might tell you, the dark side's equally important. And there's a whole lot of things that don't emit light, but do have a lot of mass and a lot of energy and do emit gravitational waves. So gravitational wave astronomy, which takes off the moment gravitational waves are really discovered, opens up a whole new view on the universe and the things in it.
Seeing gravitational waves is literally like a new set of lights going on in the universe. We can now see the dark things. So we can see black holes. Conceivably, over time, we would get to see the dark matter using gravitational waves it emits. Something excites me in particular is that if we can detect gravitational waves with enough precision, we will literally be able to look back to the Big Bang and see what happened at the moment the universe began.
Very exciting stuff. Well, I sat with many of you this morning while we heard the announcement that gravitational waves had been detected for the first time, and I certainly could sense the excitement in the room. This is obviously a very big deal. Rumors have been circulating for some time now that this was coming today, so I think we should start by putting this in context. Neil, let's start with you. What did we hear this morning, and why is it so important?
It's almost difficult to put this into words, how important it is. It's a culmination of at least 100 years of thinking, more like 200 years, in fact, because it really dates back to Michael Faraday's thinking. Faraday, in thinking about Newton's law of gravity, realized or had an intuition that it really made little sense for the force on the Earth from the sun to be felt instantaneously. So he had a thought experiment: what if I moved the sun? Would we see the force holding the Earth in orbit changed instantly, or would it take time to reach us from the sun? And in his view, it made no sense for forces to propagate right across the universe instantaneously. They must actually travel. And in fact, Faraday's insight led Maxwell, when he wrote down his equations, to search for waves which carried the electrical and magnetic forces through space. It was actually the insight from gravity that led to Maxwell's discovery of waves. And then in time, Einstein was inspired by both Maxwell and Faraday to construct a theory of gravity. And he wasn't surprised to find that his theory of gravity had these waves. That's how the influence of gravity propagates through space. So, that was in the last century, mainly. And then this century, I think for, roughly 50 years after Einstein, people thought this is just so difficult to measure. The effect is so small, we can't even try. Some very brave people started in the 1960s, Joe Weber, to make devices that might detect gravitational waves, and it's been a 50-year effort to finally culminate in what we saw today. And what's so amazing today is that the signal is just so beautiful. Usually when you detect something for the first time, it's ambiguous, it's messy, it's barely above the noise in the data. Not at all. This is just screaming at us, gravitational waves. So it's a completely amazing day in the history of physics.
Luis, I know that you study gravity. What do we learn about gravity from today's news? What does it tell us?
So we know a few things. So one is that gravitational waves are real, that these objects, when they collide, they produce such a strong influence on the space-time that we can actually go and detect it and analyze what's going on and what was the source that produced it. When I think of today's announcement, I see three results, each one of being so important. So one is the gravitational waves are real, we can detect them. We more or less have the theory to go after them, and eventually when we get more and more data, we may actually begin to see, hopefully, departures, and then that will guide us in the search for what replaces general relativity. We also learned that black holes exist, and this is the most direct evidence we've ever had of black holes and their nature, how they behave when you perturb them, how they ring down to its quiescent state, and that quiescent state is very well described by a Kerr solution. And also that nature somehow finds a way to form this system that has such a high mass in the stellar mass regime. And in more detailed way, that it has a very particular configuration of those black holes when they come together because of the final black hole that it forms. So any one of those results, I would have more than happy mortgaged my house for. And now we get three at the same time.
Well, and tell us a little bit about these black holes that we've learned about today. What do we know about them?
So we know that they have about 30 solar masses. Two of them have come together. It's very interesting that they had that mass and not a bit more, because had they had maybe 50% more mass, we wouldn't have seen it, because LIGO has a particular window in which it can actually see black holes. So these black holes only last very, very little in the window of LIGO, 0.2 seconds, and essentially they're gone. So their very high mass also made them, the signal, as Neil was saying, very, very strong. We're able to see them to a very far distance. And that these black holes nature found a way to produce them in such a way that either they were initially not very highly spinning, or if they had spin, the spins were arranged in a very peculiar configuration so that the final black hole has the spin that has been communicated in the paper.
And this merger that we've detected today actually happened long, long ago. How long ago was this that, we're looking back in time to what point?
Oh, the redshift is 0.09 or something. It's over a million years ago. Over a billion years ago.
Over a billion years ago. That's pretty incredible to think we can sort of look back in time to that distance. The signal, as you said, the gravitational waves were thought to be so weak that perhaps we were never going to detect them. Latham, can you talk to me a little bit about how scientists have managed after something like 5 decades to actually find these signals? What made that technologically possible?
Yeah, I mean, somehow for me it was one of the most striking things was just thinking that they mentioned this in the press conference earlier today, that Einstein, had analyzed the situation and decided, the person who had who would most want the signal to be visible, analyzed it and decided it would never be conceivable to measure these things, and here we are, like really several human generations later, detecting them. It's really amazing. It was a series of very ingenious technological insights. There was the sort of first interferometer invented in the early 70s by Rainer Weiss, who was one of the people who spoke at the press conference this morning. But then a series of it really took a whole series of follow-up ingenious experimental ideas to find an experiment that could shield out more and more all of the residual noise that would affect any ordinary experiment, and see this incredibly tiny effect. And then beyond that, it was just it was the painstaking work of roughly 1,000 people over decades to get it down. So, I mean, there's no simple answer about what got us here, but it was a mixture of a handful of very brilliant ideas and just tons of work actually building instruments precise enough to put each of those ideas into actual fruition, and not have the idea be swamped by other unexpected signals or noises that could have ended the whole game. Somehow that's one of the most exciting things, is just that it's one thing to say in theory 4 decades ago, and then 3 decades ago, and 2 decades ago, that we think we can build this instrument that sees so many orders of magnitude, sees things with so many orders of magnitude better precision than any instrument that we had built before. But then, to actually have it go forward and have no unexpected problem crop up that was a showstopper is, that's amazing.
Explain why we needed 2 of these detectors to see the result.
So I guess that's related. They're looking for a very, very tiny signal, and like Neil said, this first signal that they saw, it's really wonderful news. It's really a whopping signal. It's so big you can actually see it by eye, which. But even if you can't see the signal by eye, even if it's so small that to the human eye it would look kind of buried in the noise, there are still techniques you can use, statistical techniques to detect it. But with these very small signals, you just have to be very worried that you could mistake what you think that you could mistake some sort of noise, some sort of experimental error for a real signal. And so that's one of the reasons it's the fact that they saw such a whopping signal, but then also that they saw it in 2 independent detectors at the same time, or in fact not at the same time, with a slight time shift, which even tells you about, which first of all tests the idea that gravitational waves really do travel at the speed of light, but also just gives you much more confidence that what neither detector saw was a fluke.
Beyond that, does it also help us locate where the signal came from? Can one of you talk to me a little bit about that? Luis?
Sure. So as they were saying this morning, LIGO is essentially a set of ears. So we have 2, And in order to do a good localization, we need at least 3. So the 2 detectors that were functioning in this run allow to position a sliver in the sky where the signal was coming from, but that was still too large. Eventually, we would like to have the ability to know what patch of the sky should we be pointing every single telescope there is out there to try to see what else we can learn from the systems. That will come later down the road when Virgo joins. Hopefully in July, there will be a new run that will actually have the Italian detector, the Italian-French detector in addition to the 2 American detectors. And a few years later, there will be 2 more. And that will give us a very important network, which eventually will let us identify the sources in the sky within a 5 square degree patch. And that would be very, very important to reduce serendipity or remove serendipity from astronomy, at least for some sources.
Mm-hmm. I'm very excited to talk about the applications and what we'll be able to use this for going forward in astronomy. But Mina, I want to ask you about that chirp we heard this morning. There was a lot of excitement about that little noise that we heard. What was that chirp? Everyone was calling it the ringing of the universe. What did we hear?
So what we heard is the frequency of the gravitational wave as that changes as the black holes come together. So the frequency is inversely proportional to the distance between the black holes. So as they come together, the frequency goes up. And as also they come together, their gravity becomes stronger, so the intensity goes up. So that's why you saw this chirp, you heard this chirp. And in fact, for the distances, which are of order of a few tens of kilometers, turns out the relevant frequency is in a few tens of hertz up to hundreds of hertz that we can actually hear. It falls right in the dynamical range that the human ear can pick up. In fact, and I'm using fact, if we were maybe in, I don't know, maybe sometime in the future, perhaps we could put a spaceship in orbit around such a coalescing object, a certain safe distance away, and we could actually hear the gravitational wave, detect the gravitational wave with our own ears. Not me, gracious.
I don't think I'll be volunteering.
No, but there is. We have actually the human ear has a fantastic dynamical range. In fact, it can have can detect fractional changes of pressure almost at the level of 1 part in 10 to the 10. Which is 1 part in 10 billion. So, yeah. So, yes, of course, that's very futuristic, but it gives you an idea that that's why it is quite accurate that they put it as a chirp, of course, enhanced by several orders of magnitude. Yes.
That's amazing. It's just incredible. One of the comments that we heard this morning was that if Einstein had been around today, he would be beaming. Certainly, he never could have predicted. Well, I have no idea whether he could have predicted that we would get to this point, but what does it mean for his general theory of relativity in the field of physics? Neil?
I'd say it means even more than that. There's something very mysterious about the universe, which is our capacity to understand it. And here we are discussing an event 1 billion light years away, with a theory invented on the basis of prior physics and theories like Newton's theory of gravity, and a lot of logical argumentation. And this theory sort of emerged as more or less unique. It's quite hard to vary Einstein's theory. It's very predictive theory. And what do you know? It's correct. So I would say this tells us something about our own ability to understand the universe. And we know that following that understanding, we are able to use the understanding to do things. The discovery of radio waves at the end of the 19th century was made following Maxwell's prediction, or explanation of light and then prediction of radio waves. This is rather similar. So we've found another dark form of radiation. We understand it with incredible precision. We can use it. Not just to see the universe, it's conceivable in the future we'll use it for other things. It's an amazing prospect.
Well, again, one of the comparisons made this morning was to Galileo looking through a telescope, and I think that it seems that there are so many things that we can now learn about our universe now that we have proven that we can detect gravitational waves. Luis, would you like to talk to us a little bit about that? What does it mean going forward?
So in order to do that, maybe I would like to start by going backwards. So in 1918 or 19, there was this mission by Eddington that went during the solar eclipse and that tried to measure the bending that light would suffer as it goes through near a massive object. So they were able to measure that. That was one of the main predictions of general relativity. The two things could have happened in that mission. We could have gotten something that was completely different from the predictions of general relativity. That would have meant pushing theory forward, because we knew there were cracks in Newtonian theory. General relativity was supposed to supersede it, and then this would have told us general relativity was not complete. We had to modify it to make it consistent with observations. That was not what happened. Instead, we got exactly what the theory predicted, but then we turned lensing into this amazing tool that we have used to detect that there is this very mysterious matter out there, which we call dark matter, that has a significant impact in the evolution of our universe. And we are even using it to discover planets. So this is exactly the same thing. I was actually joking a few minutes ago, saying, well, maybe we should start calling the years measured from after gravitational waves. So I'm proposing AGW as a new measure, because this is a new, there is a completely new game. From now on, we're going to, anything we do that is relevant for any astrophysical process, we have to ask the question, well, what can we do if gravitational waves were produced by such an event? And how much more can we learn? So the impact is going to be across many fields, not just gravity, the understanding of gravity and astrophysics. It also is going to impact things like dark matter, things like what Mina is working around. And we're only just beginning to scratch the surface. So I'm very much looking forward to what's coming next.
Well, Mina, talk to us a little bit about that. We hear so much about the search for dark matter, and it remains a mystery. Now that we can detect gravitational waves, will that aid us in our search for dark matter?
It could. So, in fact, a few years ago, we had this proposal taking advantage of a mechanism that is predicted within the framework of general relativity. It goes by the name of Penrose process or superradiance, that tells you that under certain conditions, the black holes can be populated around them with particles. Those particles can be the dark matter of the universe, and those particles will produce gravitational waves. For the parameters that are relevant, turns out the frequencies that these models predict, it falls in the optimal range for advanced LIGO. So now, given that we have established that there are black holes, it also gives us a new avenue on the theory of an avenue to tell us what dark matter could be. In fact, the dark matter candidates that can be detected in this way, can be searched for in this way, have been looked for in the lab over the past 30 or 40 years. And what we realize now, we were given this new tool, hey, you can find them in the sky, which is pretty amazing.
So how would we go about doing that? How would we go about detecting something like that?
So the signal comes, okay, so I'll try to explain as simple as I can. The signal comes because this superradiance process causes the black hole to be populated with many particles around them. Actually, we're talking about an exponentially large number, billions of particles, that all sit in bound orbits. And these bound orbits, if you look at them, they look a lot like a hydrogen atom. If you go to a regime, in fact, where gravity is not very strong, the Newtonian potential is very similar to the electromagnetic potential that binds the atom. So the form of this bound state between the black hole and these particles looks like a hydrogen atom. So if you have a hydrogen atom, you can have transitions between different atomic levels, like you do for atomic physics, and you do atomic spectroscopy. So you can do black hole spectroscopy. And this produces very monochromatic gravitational wave radiation that would appear at advanced LIGO. It also has other consequences as well. This process spins down the black holes. These binary searches that are being done now, and in fact, perhaps even the event that they have measured now, if we know with enough information, the information we can extract about the initial spin, how fast the black holes were rotating, can give us information indirectly about the nature or constraint this particle.
Amazing. Latham, would you tell us a little bit more about some of the other things, I guess, we could find in our universe, other surprises that might be revealed through gravitational waves?
Well, I mean, so for me, one of the important things to say is that it just we don't know. I mean my favorite example of an analogy with today's detection is with the invention of radio astronomy after the Second World War. That people like Neil was saying, they already began to detect, and people like Tesla began to detect and manipulate radio waves already at the end of the 19th century, and they already could have begun to build telescopes then to look up at the sky, radio telescopes, instead of the light telescopes that we use. But there was a general impression among astronomers that it wasn't worth doing because there was nothing to see. They thought they knew what was out there. There were stars, and we know that stars emit very weakly in radio waves, and so if you built a telescope, you would just point it and see nothing. You would maybe see radio waves from our sun. And so for 40 or 50 years, nobody built radio telescopes, and then finally when they did, after the Second World War, there was a flood of all sorts of crazy discoveries. They discovered the cosmic microwave background, which is this sort of cosmic selfie that the universe took of itself 300,000 years after the Big Bang, and they discovered these things called pulsars, which are basically giant atomic nuclei that weigh as much as our sun and are whipping around, emitting a beam into space like a lighthouse. And they discovered quasars, which we now know to be supermassive black holes, 1 billion times as massive as our sun. They discovered all this stuff that you would have been crazy. People would have called you crazy if you would have suggested it before the advent of the radio telescope. But as soon as you turned it on, it was out there. And so so I think most people, including frankly myself, think nowadays we more or less know what's out there, and that the exciting things that LIGO will see will be merely ginormous black holes merging to form other black holes. But I mean, it's just a historical fact that often you see wilder stuff, and so that's one of the most exciting things for me about.
Maybe I can add one comment. I mean, yes, we have been learning a lot about our universe through the electromagnetic spectra, and very recently also a little bit through particles, because we've discovered neutrinos that come from out there. But in my mind, it's always been like I'm sitting outside a theater and people are coming out, and I'm trying to guess what happened in the movie by just looking at the expressions, and if they come out. Gravitational waves, because they can probe so much deeper, they can get very close to the source. Now it's buying at least the plot of the movie for me. And I can have much more information, as opposed to the standard examples of particle physics, where you know what you put in, you know what comes out, and from there you can tell a rather complete story. When we watch at the skies, we only get what is coming out. We are not really sure what went in. And gravitational waves will provide this very crucial complementary information, and will let us begin to paint a much more complete picture of some of the most mysterious events. So at the current moment, there is this very interesting phenomena which we call short gamma ray bursts. These are these flashes of gamma rays across the spectra that tells us that the process is releasing a ton of energy. We think there is a black hole deep in the middle playing an important role, but we haven't been able to make contact with that. Gravitational waves will allow us to do that. So I'm looking forward to very soon, LIGO and the other partners in the network detector will allow us to finally unravel that first mystery.
Neil, can you talk to us a little bit about how gravitational waves might be able to tell us something about the early universe?
Yes, this, of course, came to public's attention over a year ago when the BICEP team claimed to have seen gravitational waves coming out of the Big Bang. And this was felt by some, including Stephen Hawking, to be compelling evidence for a process called inflation, which happened in the early universe. And this is a burst of exponential expansion of the universe driven by a strange form of energy, which remains hypothetical, which would have generated gravitational waves. And then BICEP was claiming to see them rather indirectly through their effect on the plasma of radiation, and they cause a polarization of the light coming to us. So that claim ultimately turned out to be wrong. There was a confusion with dust in our galaxy. But in fact, what happened was very positive, because this false claim resulted in many other experiments chasing after the same signal. And so it could be that in the coming even 2 or 3 years, other experiments will either see the signal or disprove it. And this will tell us a lot about what happened at the Big Bang, whether inflation was correct or some other theory was correct in its place. Now, with what's sort of even much better than all of that is that LIGO's detection is absolutely direct. I mean, it really is detecting the gravitational waves themselves, whereas BICEP was relying on this indirect probe. And the amazing thing is that successors to LIGO will be able to detect gravitational waves coming directly from the Big Bang singularity to us. And so literally we will be able to use these new eyes we've got, i.e. gravitational wave detectors, to see what happened. How did the universe begin? Suddenly it becomes a scientific question where we can not only make theories, but we can test them in very direct, clean observations. So that's just a totally awesome prospect. It's the biggest question in science. Where did everything come from? And we are, on the threshold. One can't say exactly when we'll have the technology to do this, but it may be, 20, 30 years away. We'll literally be able to look for, what happened at the Big Bang.
That's pretty incredible. In order to get there, I guess we will need to continue to develop our technology to detect gravitational waves. And so we should talk a little bit about what is coming, some of the potential next generation detectors that we might see. Latham, can you tell us a little bit about, beyond LIGO, how we could look for gravitational waves?
There are really a lot of different things going forward. I mean, one thing that really merits a mention is a wonderful proposed experiment, space-based gravitational wave detector called LISA or ELISA, which is a proposal for three satellites orbiting around the sun, and they bounce laser beams back and forth in a similar way to how the LIGO detector bounces laser beams back and forth between its mirrors. And any tiny ripples in space-time passing through the solar system will cause the distances between those satellites to change a little bit, and by interfering lasers, they can pick up those changes. And so that would be an example of a fantastically sensitive experiment, and it would also look at a very different frequency range from LIGO. So it's a bit like in ordinary astronomy, if you look up at the sky with optical telescopes that see visible light, you see one sort of objects, or you see them in one sort of way. But then if you look with radio telescopes, you see very different objects, or the same objects, but very different aspects of those objects. And so there's a similar thing in gravitational wave astronomy. LIGO has now opened up this window of frequencies where we can now see gravitational waves. And one of the most important things to do going forward is to develop other windows where we can also see gravitational waves. So for example, the LISA detector would be able to see two of these supermassive black holes merging to form a giant supermassive black hole. That's a process that never emits gravitational waves high enough for LIGO to see, but is still some fantastically interesting thing that's going on out there that we would like to see. So that's one sort of thing. And then I guess another thing is just that there's really enormous potential for improving gravitational wave technology to make it more and more sensitive. Here we are, again, just 100 years after Einstein concluded that it was forever impossible to detect these things, now able to detect them. And so at the moment, it's very hard. It's a real triumph of human achievement to have reached the sensitivity to have detected them at all. But I mean, over decades, things really make progress that would seem unimaginable. So there are all sorts of clever things you can do, many of which are already sort of under development and people hope to put them into play in the LIGO detector, for example, for improving the sensitivity of these detectors and allowing you to dig even deeper into signals, see even further out into the universe. Those are those.
It's worth mentioning that there is already an experiment that's running. There's the Pulsar timing array. Oh, yeah. So this is an experiment that uses nature's best timekeepers, pulsars, that's been in a very steady rate, and looks at gravitational waves whose frequencies, whose periods are years, something of an order of a year. And the way these are the gravitational waves that pass through the Earth, and they use the effect that Luis mentioned earlier, the time delay, that locally the strength of the gravitational wave locally on Earth changes the arrival time of the light of the signal pulses from those pulsars. So they are adding more and more pulsars in their network over the next few years, and they have a great chance of seeing something. There is other technologies actually that will cover possibly every decade in between the Pulsar timing array and LIGO. There is LISA. There are also several ideas out there that people are currently exploring that want to use atomic interferometry and atomic clocks to detect gravitational wave radiation. So these are both Earth-based detectors, but they're also space-based proposals that have been pursued. So this is just the beginning of an era. We saw one event. If you read the paper that just came out, you'll see that the expected event rates could be thousands per year in the next few years once LIGO reaches design sensitivity. So it's truly the opening of a new field. And the future is very bright. We don't know what we'll see. Every time we've looked at the universe at a different frequency, in a different wave, we found something new. So surprises are bound to come.
It's just incredible. Our time is running down. I would love to hear from any of the panelists, any final thoughts on what this means for the field of physics and astronomy. We're obviously at the dawning of a new era, and there's a lot to be excited about.
So maybe I can say something. So just maybe a sociological afterthought. I mean, general relativity, the field that essentially brings this detection today possible, was for the longest time the punching bag of theoretical physics, because it didn't have as Neil was saying, the initial calculations were, well, any experiment would just take so much that who would go there? One of the most famous physicists of the 21st century famously went to a meeting of general relativity and afterwards wrote a letter to someone and said, remind me never to come back to one of these meetings. So for decades, I mean, it took a long time to go there, but it also shows that long, steady investment in a particular area that has promise eventually will pay off in a huge manner.
Wonderful. Well, this is obviously a great announcement today, and it's been such a pleasure to chat about it with our four panelists. I just want to thank once again Asimina Arvanitaki, Latham Boyle, Luis Lehner, and Neil Turok from the Perimeter Institute here. And I should add also that the Perimeter Institute has put a lot of educational resources and classroom resources on the website. So any teachers who want to share this with their students or anyone else who's curious should really check that out. And again, any questions over social media, on Twitter and Facebook, there are Perimeter researchers who are there to answer. My name is Kate Lunau. I am a science writer, and once again, very glad to be here today to talk about gravitational waves and a whole new era of physics and astronomy. Thank you so much.